A major Russian oil refinery that handles about 6% of the nation's total processing capacity collapsed from full output to zero in just minutes after a sudden night strike. More than 300 long-range drones from Ukraine lifted off from hidden launch points across forests, highways, and industrial rooftops before crossing deep into Russian airspace. Their target was Kirishi, a site located far from the front line and long viewed as one of the safest points in Russia's energy network. A facility worth billions fell to drones that cost roughly $50,000 each, and the attack pushed Russia's air defenses into a state of confusion. S-300 and S-400 systems were dragged upward by high-altitude decoys while Buk and Tor crews fired at mid-level targets until their launchers ran dry. MiG-31 pilots searched the sky for threats that were actually flying only a few dozen meters above the ground, hidden inside radar clutter that their sensors were never designed to penetrate. The contrast was stark. Cheap and flexible weapons moved with precision, while traditional defenses reacted too slowly to stop them. The number of drones is not the most shocking part. The real surprise comes from the coordinated tactics that let them break through. 1,000 kilometers of layered defenses. It raises a question that now hangs over every strategic site in Russia. If Kirishi can be breached so easily, then where is truly safe? More than 300 long-range drones formed the backbone of a complex strike plan. And this plan began with a wide network of hidden launch points that stretched across Ukraine. Operators worked inside bunkers carved into forest edges, on top of quiet industrial buildings, beside dark highway rest stops, and at mobile sites that moved shortly before each launch. These locations allowed the teams to fire without giving early warnings to Russian sensors, and the scattered pattern made it impossible for a single radar sweep to detect the entire liftoff sequence. Each drone carried preset routes that kept them low and quiet until they cleared Ukrainian territory. And the sudden rise of so many flights created a wave of movement that was hard to track. The Kirishi strike group was timed to leave later than many of the other flights, yet it was programmed to fly faster so it could reach its target at the exact moment the main swarm reached other regions. This careful timing was designed to create a single pressure point across a wide area, and Russia had to decide whether to defend Moscow, Bryansk, Smolensk, or the refinery that processed a large share of its fuel. The decision window was narrow because the drones were set to reach their assigned points within the same 20-minute period, and any delay from the defenders risked letting several groups slip through key gaps. This approach forced Russian air defense to spread its attention across multiple regions, and each shift in focus weakened the protection of another sector. Radar crews turned their antennas to cover rising tracks on one side of the map, while losing sight of low objects moving in another direction. And these shifts opened small holes that could not be closed quickly. Missile crews faced the same challenge because each launcher could only follow a few targets at a time, and the number of contacts grew with every minute. Fighter pilots also faced a confusing picture because they had to choose between responding to high-altitude signatures or chasing reports of small objects moving slowly near the ground. Ukraine built this plan to ensure that no Russian unit could focus on a single group of drones for long, and the size of the swarm played a role in stretching the response thin. The real advantage came from how the flights worked together because each group acted like a gear inside a larger machine. When one set of drones moved toward a major city, another set slipped through a quieter path that had fewer sensors watching, and the movement created a shifting pattern that was hard to predict. The results showed how coordination across many routes can weaken even a thick defensive wall, and the question now stands for viewers who follow military affairs. Which factor created more danger for Russia during this strike? The number of drones in the sky, or the way they were linked inside one unified plan? The answer may shape how future militaries prepare for long-range threats, and it may also change how nations choose to protect critical energy sites. The FP-1 became the center of the strike because it offered long-range performance at a very low cost. And this combination created pressure on every Russian defense layer. The drone used a small two-stroke engine that cost only a few $100s, yet the system could travel up to 1,600 kilometers with steady speed. And the navigation package linked GPS, GLONASS, and a radar altimeter to keep the route stable even when jamming was active. This mix of signals helped the drone hold its course across open terrain and industrial zones. And the steady flight profile made it difficult for Russian sensors to predict where the next turn would happen. The design was simple, but the effect was serious because operators could launch these drones from deep inside Ukraine without relying on complex support crews. The warhead carried by the FP-1 added another level of danger because it held enough explosive power to break steel frames and damage refinery towers that handled extreme heat. A hit on any major pipe could force a shutdown, yet a strike on a pressure unit or tower could trigger a chain reaction that spread across the facility. This is why each drone carried a payload that matched the needs of a deep strike, and the low price of each platform made it possible to send many units toward the same target. Russian commanders understood that one drone slipping through could cause major damage, and this forced them to decide whether to fire high-value missiles at incoming tracks or hope that the threat would miss its mark. The financial pressure created by the FP-1 shaped the entire defensive response because each interceptor missile cost far more than each incoming drone. If defenders launched too many shots at low-cost targets, they risked running out of ammunition before the wave ended. And if they held fire, they risked letting a drone reach a critical point inside the refinery. This dilemma grew with every passing minute, and FP-1 units kept moving at steady speed, which meant many of them would reach the engagement zone at the same time. The volume of threats made every choice risky, and the stress on the Russian crews increased as screens filled with new contacts. The flight path added another layer of complexity because FP-1 units flew extremely low, and the ground clutter made the tracks hard to separate from surrounding noise. Radar beams struggled to pick drones out of the background because trees, buildings, and terrain features reflected signals that looked similar to a fast-moving object. This confusion forced radar operators to rely on incomplete data, and the limited clarity slowed down decisions on whether to assign missiles or call in interceptor aircraft. MiG-31 pilots could not easily spot the drones because the targets stayed close to the surface, and the search patterns of the aircraft were designed for high-altitude threats. The challenge for Russia grew as the strike continued because the low-altitude path left very little time to react once a drone appeared on a scope. The FP-1 did not need to break through a sophisticated shield. It only needed to reach the short-range zone around the refinery where ground clutter became even stronger. And once inside that zone, the defenders had few tools left that could hit a moving target without risking damage to their own facility. The three-layer formation used in the Kirishi strike became the key that unlocked the Russian air defense network because each layer forced a different reaction and created pressure on systems. The top layer began with Mugen 5 drones climbing to altitudes between 3,000 and 5,000 meters. And these flights carried reflectors that made them appear much larger on radar screens. The strong reflections pulled the attention of S-300 and S-400 crews because the signatures looked similar to high-value threats. The long-range batteries lifted their tracking beams to follow the rising contacts, and this shift created an opening beneath them because their radars were now focused on the upper part of the airspace. The middle layer followed with UJ-22 drones flying at moderate altitude, and these units acted like shields for the rest of the formation. The tracks appeared inside the range of Buk and Tor systems, and the Russian crews had to assign interceptors to stop them. Each missile fired at a UJ-22 was one less missile available for another target, and the process drained the defender's stock with every engagement. Pantsir batteries joined the fight when the UJ-22 drones entered their zone, and the rapid-fire missiles chased targets that kept a steady line toward the refinery. The middle layer increased the pressure on every radar operator because the number of contacts kept rising, and the crews had to decide which object posed the greatest danger. The bottom layer carried the FP-1 drones that posed the real threat, and these units stayed at altitudes between 10 and 50 meters throughout the approach. The low flight path made them disappear inside ground clutter because trees, roads, and buildings created heavy noise on radar screens, and Russian operators could not easily separate the drones from the environment. Ground-based systems struggled to detect the low tracks until the drones were already close, and by that point the window for a clean shot was extremely narrow. Fighter pilots had no clear view either, since the search patterns of aircraft like the MiG-31 were built for high or medium altitude interception. The slow and steady motion of the FP-1 units blended into the landscape, and this blend gave them enough time to cross the final distance. The top layer forced long-range systems to look upward. The middle layer drained missile supplies and distracted operators, and the bottom layer moved forward with little interference. Russia had no unified defense that could handle all three layers at the same time, because each system was built for a specific altitude and threat type. This mismatch created gaps that widened as the formation advanced, and each step of the approach made the next step easier. The breakthrough toward Kirishi depended on a precise move against an S-300 radar site, and this move began when a group of decoy drones climbed high enough to trigger the main tracking beam. The radar locked onto the bright signatures because the reflectors on the decoys made them appear larger, and the Russian crew treated the contacts as major threats. While the radar followed the rising objects, one drone transmitted the timing pattern of the frequency cycle back to the rest of the formation. This step mattered because the S-300 system needed to reset its hopping sequence, and during that short reset it stopped transmitting. The decoy that sent the data was destroyed soon after, yet it had already delivered the information that the main group needed. Ukraine programmed the incoming drones to adjust their altitude exactly in sync with the half-second pause in the radar cycle. The reset created a moment when the radar was effectively blind, and the formation used that window to dip lower and move into the zone where the beam no longer tracked them clearly. The drones turned this gap into a shield, because the system could not update their positions once they were below the beam's reach. The radar resumed operation after the reset, but the main group had already shifted into a part of the sky where reflections blended into natural noise. The Russian crew saw shapes that looked like weather effects or scattered objects, and the screens showed returns that were too weak to classify. The radar operators could not build a clear track from the mixed signals, and without a stable track, the system could not guide missiles toward the correct point in space. The defense network tried to coordinate with other units, yet the altitude shift happened too quickly for the information to move through the chain of communication. The lack of clear data forced the crews to wait for stronger signals, and this delay let the drones move deeper into the protected area. The success of this tactic came from the way the drones used the environment and the radar's own architecture against it. Terrain features created echo patterns that hid small objects, and the half-second pause pushed the drones into a position where the radar's strength could not reach them. Russian operators faced a sensor picture filled with clutter, and the pulse reflections shifted too quickly for them to regain a locked track. Is the weakness caused by a design flaw inside the Russian radar? Or does this moment show how new tactics can turn even powerful equipment into vulnerable targets? The final approach to Kirishi showed how the last defensive ring collapsed under the weight of coordinated pressure, And the collapse began when several UJ-22 drones entered the zone covered by Pantsir units. The Pantsir crews faced a rising number of mid-level contacts, and each launcher could only follow a limited set of targets at one time. The UJ-22 drones kept a steady path toward the refinery, and their movement forced the crews to fire in rapid cycles because ignoring them risked letting an unknown threat slip into the protected airspace. Each missile fired at these drones reduced the stock of the battery, and the drain created a moment when the launchers had no ready missiles left in their tubes. This window opened as the FP-1 units approached the refinery, and the timing placed the main threat at the edge of the engagement zone when the Pantsir systems were shifting to reload. The arrival of the FP-1 drones at low altitude created an immediate problem for the Russian crews because the drones were moving inside a narrow band where most short-range weapons could not operate safely. The FP-1 units stayed below the angle required for the Pantsir guns to depress, and the fire control systems could not target them without risking hits on nearby structures. The ground around the refinery held multiple fuel lines and storage tanks, and any misfire could trigger a chain reaction. This forced the crews to hold fire, and the absence of a clean firing solution allowed the low drones to move deeper into the critical area. The defensive zone at this point became a blind spot, because the sensors could not see through the clutter created by the refinery layout. The Derivatia PVO 57mm system stood as the last line of defense, yet it faced its own limitations once the drones moved below a certain height. The system used programmable shells that created controlled bursts, but the shells needed enough distance to form an effective pattern. A burst fired too close to the refinery risked spraying fragments across fuel storage areas, and the safety protocols prevented the weapon from firing below a set altitude. The FP-1 drones crossed that threshold before the system could finish its firing cycle, and the barrel locked when the drones dipped into the lower band. The operator could track the objects clearly but could not release another round because the fire control rules blocked any shot that might endanger the site. This lockout froze the weapon at the worst moment, and the drones continued moving toward the core facilities. The first FP-1 struck the CDU-100 unit, and the impact cracked several major pipes that carried high-temperature crude. The rupture sent superheated material into open air, and the sudden contact created a wave of pressure that spread through the surrounding equipment. The shock weakened support frames and forced valves into failure positions that accelerated the spread of heat across connected systems. The second FP-1 hit Tank 47, and the explosion threw the tank's roof into the nearby administrative building. The loss of Tank 47 removed a key buffer area inside the refinery, and the burning fuel spread across the ground. The combination of heat, pressure, and ruptured lines triggered a BLEVE event, and the energy release tore open additional storage units. The shock traveled outward through multiple structures, and the cascading failures shut down the entire site. The refinery's capacity fell from hundreds of thousands of barrels per day to zero, and the damage required months of work before partial operations could resume. The scale of the destruction now raises a question for every viewer who follows military and energy issues. Can Russia repair Kirishi within the next year? Or has the strike pushed the facility into a long and uncertain recovery? A major oil hub that once fueled a large share of Russia's energy network has now gone dark, and it happened because more than 300 long-range drones, many of them built from low-cost parts, broke through every defensive layer meant to protect it. Kirishi was not only a refinery, it was a symbol of depth and distance, a site believed to be far beyond the reach of Ukrainian strikes. Yet the attack showed that distance no longer guarantees safety in modern warfare. The real advantage came from smart planning that used decoys, timing cycles, altitude shifts, and ground clutter to bypass radars designed for a different era. The strike left Kirishi silent, And the question that now hangs over every military planner is not just how long repairs will take. The next months may bring deeper raids, wider ranges, and cheaper systems that push this trend even further. And the reaction of Russia, NATO, and Ukraine will shape the next stage of the conflict. Whether new defenses rise fast enough or whether the drone advantage grows even stronger is something viewers will watch closely. If you want more clear breakdowns of battles like this and straight talk about the weapons and politics shaping today's conflicts, like this video, share it, and subscribe to Military Force.